Hello, and welcome to the first in a short series of videos celebrating elements in crystals from Cambridge Crystallographic Data Centre and the British Crystallographic Association. Fantasy worlds have brought us amazing characters, landscapes, and stories, but one thing we can often ignore are the materials that characters rely on to complete their adventures. But not today. This video will dive into some potential real-life replacements for science fiction's creations as we consider the world according to science fiction. Some heroes need special rocks or crystals to help them on their adventures, some world-building games make use of special functional materials, and some fantasy materials just have crazy properties. Sure, we can accept that they're fictional, but what would we use if we were bringing this fiction to life? Let's start with a fantasy favourite, Adamant, a mythical material which is harder than any other. It's been mentioned in Greek myths and classical texts like the Aeneid, Paradise Lost, and Dante's Divine Comedy. But don't worry, it's also made its way into more modern fiction. One of the Rings of Power in the Lord of the Rings series, Nenya, has a gem made from adamant, and part of the Dark Tower is also made from it. Fantasy tower builders must have had a soft spot for it, because Lord Asriel's tower is also made from adamant in the book The Amber Spyglass from his Dark Materials trilogy. Adamant has gone by a few different names throughout the stories too. A material called adamantine is an extremely hard toxic metal in Dungeons & Dragons, and weapons made from it can deal damage to tough, inanimate objects. There's also adamantium, a nearly indestructible metal from the Marvel comics, which coats Wolverine's skeleton and makes up the body of the supervillain Ultron. If I had to guess, as soon as we started talking about an impenetrably hard material, you probably thought of diamond, right? Diamond is a form of carbon, but why is it so hard? To answer this question, we need to delve right down to something called the crystal structure, how a material looks at the level of atoms. The reason diamond is so hard, or as it's usually described in stories, impenetrable, is because all its bonds are strong carbon-to-carbon covalent bonds. This means it's hard to pull them apart in any direction. However, diamond isn't actually stable under normal conditions, what scientists would call room temperature and pressure. Instead, carbon would prefer to be in a different structure, known as graphite. Graphite is made up of layers of carbon atoms joined by these strong covalent bonds, just like diamond, but the forces holding the layers together are much weaker, so it's much easier to indent it. In fact, one place you might have seen graphite before is in pencil lead, where these layers of carbon helpfully get left behind on the paper to leave a mark. Luckily for users of adamant, the transformation of diamond to graphite has a huge energy barrier to overcome, so it doesn't happen on a scale humans can appreciate. Elves might spot it though, so maybe that's why they were never corrupted by the Rings of Power. One very interesting carbon-based molecule is adamantane. It both sounds like adamant and looks like it too. The carbon atoms in adamantane fit together with the same relative orientation as in diamond, but instead of being a very large lattice, the structure is cut off by these terminal hydrogen atoms to form discrete molecules. One of the main uses for adamantane derivatives is in the medical industry. Amantadine was used as an antiviral drug against various strains of flu, and it's now used to treat Parkinson's disease. Perhaps the adamant-diamond link was too easy to spot. Let's try Bombastium now. It comes from the Disney universe, and it's described as the rarest element in the world. In the periodic table, there are quite a few elements which we could give that title to. Let's take a look at some of our contenders. Organesson, tennessine, and ionium are some of the heaviest elements discovered, sitting at the bottom right of the periodic table. They're all rare, but in particular, only a few atoms of organesson have ever been produced. That might make it the number one candidate for rarity in your book, but the most stable isotope of tennessine has a half-life of just 51 milliseconds, so any atoms that are created really don't stick around very long. Ionium's longest-lived isotope has a half-life of about 10 seconds, so it's around a little longer than tennessine, but it has no uses outside research, so very few people will ever come across it. However, the rarest naturally occurring element is astatine, and since none of Donald Duck's experiments involve him creating new elements, astatine seems the best fit for Bombastium. This Royal Society of Chemistry infographic tells us that part of the reason astatine is so rare is that it's actually unstable. so once it's formed, it doesn't hang around for very long. In fact, its name even comes from the Greek word astatos, which translates as unstable. The reason for this instability is that astatine has a big imbalance between protons and neutrons, so to try and fix this, it gets rid of some internal energy through a process known as radioactive decay. Astatine's most stable isotope only has a half-life of around 8 hours, so no crystal structures of its compounds exist. In fact, very few compounds have been identified at all. However, some compounds of astatine with another element called palladium are known. Iodine sits just above astatine in the periodic table and can create palladium iodides, which are relatives of the palladium-astatine structures. They're incredibly versatile starting reagents for chemical synthesis reactions. The heavy palladium atom allows the carbon to have fewer than its usual 4 bonds, which can help certain reactions to happen extra efficiently. The final sci-fi element we're going to talk about in this video is redstone, the material used for wiring in Minecraft. It can also be crafted into several mechanical objects in the game, giving us a pretty easy real-life element to match it to: copper. Almost all the wiring we encounter in homes and businesses is made from copper for a couple of reasons. It's pretty inexpensive compared to the alternatives, it's able to be drawn into a wire or bent into shape without breaking, it's conductive, and it's fairly thermally resistive too. As well as its use in wiring, copper can also form several very useful alloys with other metals to make materials like brass and bronze. Traditionally, what we call bronze coins were made from this alloy of copper, tin, and zinc, but across the world these are being replaced with copper-plated steel instead. All the more redstone for my house, I guess. One of the most iconic copper landmarks is the Statue of Liberty, located on Liberty Island in Manhattan, New York. It was a gift from the French, and its metal framework was actually built by Gustave Eiffel. I'm sure you can guess the tower he designed. There's something strange about Lady Liberty though. Weren't we just saying copper matches the properties of red stone? How come it's more of a blue-green colour? The colour actually comes from some special protective materials which form when the copper encounters the gases and moisture in the air. Copper can react with oxygen from the air to form compounds called copper oxides, which keep reacting until this black oxide is formed. This oxide is then able to react with carbon dioxide and sulfur trioxide from the air, as well as hydroxide ions from moisture, to form the blue and green compounds which give it its distinctive colour. The statue is close to the Atlantic Ocean, so there's a very high level of humidity for the copper to react with. In fact, the combination of this high humidity and the high level of air pollution in the 1800s allowed these reactions to occur significantly faster than they normally would, developing this coating in just 20 years. It's the same process that causes copper rings and other jewellery to turn our skin green-blue when they come into contact with water or sweat. The crystal structures of malachite, azurite and brochantite, the 3 minerals responsible for the colour, are shown here. In nature, copper is found in both its free metallic state and as part of minerals like these. It's actually named after its first mining site, the country Cyprus, where the copper mine supplying the Roman Empire was located. That brings us to the end of today's video. Thanks for helping celebrate elements in crystals, and I hope this helped bring some science fiction down to earth. For more videos unpacking the elements and where we find them, follow CCDC Cambridge on YouTube, or check out their periodic table pages for more resources and ideas. You can also keep up to date by following the BCA or CCDC on Twitter. Have a look in the description for details. Many thanks to the Royal Society of Chemistry for their generous funding to complete this project. And most importantly, thanks to you for wanting to know more today than you did yesterday. See you next time!